So anyways, today we're going to be focusing in on a classic claim. I would like to be able to prove to you that log base b of n is big O of n. Now you might say, Dan, that's kind of obvious. How do I know? That should be just obvious. It's easy. Well, it's important that I give you at least one way to get there, okay? So a key ingredient to make this proof work is I'm going to prove the following claim for you. So for every integer n greater or equal to 1, it has to be that log base 2 of n is less than or equal to n. Now I must stress that there is a stronger claim you can make here, but this is all I need to make this work, okay? So to do this, I'm going to use mathematical induction. So I'm going to use the principle of mathematical induction to make this work. So I'm going to formulate this in terms of an induction proof. Now, I've talked about induction before, so I'm hoping that you'll catch on pretty quickly what we're doing here. So I'll remind you as we're going along. So this is the statement. I'm going to reformulate it in the following way. For each integer n greater or equal to 1, let L of n denote the statement as follows. So L of n is log base 2 of n is less than or equal to n. So what I need to do is prove this for all n greater or equal to 1. If we could do that, we win. We won. We've proven the claim. So I formalize the statement. So first thing I do in an induction proof is I work with the base step. So I got to start with the simplest, the first several inputs. Now in this case, I should be good enough just doing n is equal to 1 because my statement only, the way I'm going to perform the induction only relies on the previous statement, the one less input, not 2 or 3 beyond that. It should be just rather straightforward. So the base step here, this is when n is equal to 1, is as follows. For L of 1, so L of 1, so we're going to prove L of 1 is true. The statement log base 2 of 1 is less than or equal to 1 is true as log base 2 of 1. Okay, let's think about what log base 2 of 1 would be. Okay, if I have 2 to the something is equal to 1, what's the exponent have to be? What does it have to be? It has to be 0. So let's make it, so this is equal to 0, which is in fact less than or equal to 1, right? So that's the base step. Now, to get the induction step working, what I'm going to do is I'm going to show, given L of k, I want to show that L of k plus 1 also holds. So if I assume L of k holds, then L of k plus 1 must follow from it. So just as a reminder, the way this works, say if I think about Miss Kitty and I'm trying to teach Miss Kitty how to climb up to her bed, say it's on a bunk bed, I need to show, so I start off at the bottom rung. I've shown Miss Kitty how to get to the first rung through L of 1. Now what I need to do is I need to show for an arbitrary rung of the ladder how to get Miss Kitty up to the next rung. So how do I prove, given that L of 1 is true, how do I show that L of 2 is true? So the goal here is I'm going to try to reformulate L of 2 so that so I can use L of 1, which I know is true. And the idea is that if I pick any arbitrary rung, I can take L of 2 to show that L of 3 is true. Then L of 3 is true, then L of 4 is true. Or say L of k is true, then L of k plus 1 has to be true. And just like, if you imagine it's like I'm knocking off some dominoes, it's a whole row of these suite going all the way across for all integers greater or equal to 1. If we use the principle of mathematical induction. So that's how the principle of mathematical induction will get used here. So here's the induction step, or the inductive step. I'm going to show that if L of k, then L of k plus 1. So I'm going to fix some integer k plus 1. Sorry, not k plus 1. K is greater or equal to 1. So I'm going to fix for one rung. So I'm going to, for one given rung, I'm going to fix k greater or equal to 1. And I'm going to assume L of k, which, as a reminder, that's at log base 2 of k is less than or equal to k. So this is going to be our induction hypothesis, or inductive hypothesis, is true. We prove next that L of k plus 1 follows, which, remember, L of k plus 1 is that log base 2 of k plus 1 is less than or equal to k plus 1. That's what L of k plus 1 is. We have to show that this follows. So what we're going to do is we're going to start on the left-hand side. So we're going to start on the left-hand side of L k plus 1. And I'm going to take advantage of the fact that I can bound the inside of this, so the input here. So k plus 1, I'm going to bound this from above with a product. I've done a technique kind of like this before in another lesson before, but check this out. And once I have that, then I'm going to use properties of logarithms. So beginning with the left-hand side of the inequality, we could say log base 2 of k plus 1. Log base 2 of k plus 1 is what? Well, what I ideally would like to have is something that looks like L of k. So I want to make something that looks like L of k. So something involving log base 2 of k. If I can get that, then we're in good company. So this, my claim is that this is less than or equal to log base 2 of 2k. Now, if you're not convinced by this, let's just kind of work it out on the side here. Well, now remember, what I'm really saying, because logarithms are increasing functions, I have to really just compare the inputs in here. I have to show that k plus 1 is in fact less than or equal to 2k. If I can do that, then log base 2 of k plus 1 has to be less than or equal to log base 2 of 2k. So k plus 1, suppose that I have k plus 1 is less than or equal to 2k for all k's greater or equal to 1. So suppose I have this. This has to be true if and only if the following is true. Well, let's see. I have the following. Well, let's see. I can subtract off k from both sides, so I subtract k from both sides. And now I end up with 1 is less than or equal to k. And do you see how this is just saying that this has to be true for k is greater or equal to 1, right? That's what all it's saying. So that's what I'm saying, is that this is true because of this. So this is guaranteeing that this holds for all k is greater or equal to 1. Well, next, this is equal to this. So I'm just going to rewrite this in a deliberate manner. Log base 2 of k times 2 inside the input here. So for the input. But next, I'm going to apply the product rule of logarithms. So log base 2 of k plus. So I'm just going to just split this into two sums. Log base 2 of 2. So this is the product rule of logarithms. That made me possible to do this. It's not magic, it's just math. So let's do this. It's that math, okay? But what's log base 2 of 2? Okay, 2 to the what is equal to 2. What is that? 2 to the power of what is equal to 2? Just 1, and this is just 1 here. So look at this. So this is just log base 2 of k plus 1. But here's the thing. What's this? That's the left-hand side of L of k, right? But we know that that's less than or equal to k, right? So this is by the induction hypothesis. And you see that we just showed, using the induction hypothesis, we got from L of k to L of k plus 1. because, which is the right-hand side, right, of LK plus 1. Thus, LK plus 1 holds. So it also holds. Therefore, we can use the principle of mathematical induction because we have all the pieces and pieces. By the principle of mathematical induction, which I'll abbreviate as principle of mathematical induction as PMI, L of n is true for all n greater or equal to 1, and we're done. So now we know for all n greater or equal to 1 that log base 2 of n is less than or equal to n, which is all we need as the key ingredient, right? Because you actually think about it, if I wanted to prove that log base 2 of n is in fact big O of n, well now I told you that for all n greater or equal to 1, this is true, right? So I can pick n0 to be 1, and I can pick c to be 1, and that's it. It's a piece of cake, right? So let's now prove it. So let's actually put this all together now. So I'll show you this, and then I'll show you a nice way you can apply this result. So you can apply this result we just showed over here. So the next thing we're going to do is we're going to prove that log base 2 of n is big O of n. So this is a nice, pretty, I would consider it a rather important relationship that logarithmic functions have with linear functions. So we have to do what we usually do. We need to lay out the game plan. To prove the claim, I was about to say, to prove the claim, we find constants. C, which is a positive real number, and n0, which is a positive integer. Such that log base 2 of n is less than or equal to c times n for all n greater or equal to n0. So like I said, I'm just going to pick c is equal to 1. And then observe by the previous theorem that log base 2 of n is less than or equal to n for all n greater or equal to 1, right? Pretty wonderful, right? So we have all the key ingredients. So now I can just simply choose n0 is equal to 1. Therefore, by the definition of big O, we have that log base 2 of n is big O of n. And we've established this nice classic property. That's pretty wonderful, right? So we've sorted that out. So now we know that log base 2 of n is big O of n. And I must stress that this proof is not very hard to modify for arbitrary other bases, because the way the proof worked before is not that much different. So notice that the way I did things with the base didn't really matter a whole lot, right? Next thing I would like to talk about is a basic application of the following results. So like what we just talked about here. So the next thing I want to do is I want to prove to you that n is big O of 2 to the power of n. So I would like to bridge those two. So next we're going to prove the following. So next we're going to prove that n is big O of 2 to the power of n. You're going to see that I already have all the machinery to make this work. So watch how slick this gets. So we just got to find the constants, right? We find the constants c, which is a positive real number, and n0, which is a positive integer, such that for all n greater or equal to n0, n is less than or equal to c times 2 to the power of n. I'm just going to pick c is equal to 1, and we're going to proceed in a way that should remind you of something. Pick c is equal to 1. We're going to apply logarithms to both sides. To both sides of the inequality. Both sides of the inequality. Then we find n0 so that log base 2 of n is less than or equal to log base 2 of 2 to the power of n. What's this? Well, the power rule says you can pull this n out front, and then we have log base 2 of 2, which is equal to 1, right? This has to be found such that it's true for all n greater or equal to n0. But look, we already proved this, right? We already know that log base 2 of n is less than or equal to n for all n is greater or equal to 1. So let's just say that. By the above property, log base 2 of n is less than or equal to n for all n greater or equal to 1. So choose n0 is equal to 1. There. Now we got the two constants. Therefore, by the definition of big O, n is big O of 2 to the power of n. Piece of cake, right? It's just a direct application of that proof we got, of our claim that we proved with mathematical induction. Is that wonderful? So now we have a way we could bridge to the exponential functions by just simply using this very basic claim.